So of course, there are other equations of state that we could use. And I just showed you the ideal gas. We will mostly use the ideal gas. I just want to make sure you're aware of the other ones that are commonly used. There are more than just these. There are many, 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 many more. You've probably heard of the van der Waals, and if you've not, that's the most commonly cited one to show you non-ideal gas behavior. And it looks like this. There's also the Redlich-Kwong equation of state, which is very similar in scope and in appearance. These A's and B's that you see, which are new things here, those are material-specific constants. So you can look them up. So water has its own, and oxygen has its own, etc. And the back of the book has them. So if you wanted to use the van der Waals equation of state to find the pressure for water, water vapor, you could go look up the A and B, put them in, they'll be just numbers, and then you can use this in the same exact fashion as you'd use the ideal gas equation. And same thing with the Redlich-Kwong. There's also the virial equation of state, which isolates PV and RT. So basically, we said that PV is equal to RT. If I divide PV by RT, if it was an ideal gas, this whole thing would be 1. But we say that a non-ideal gas would have some sort of an expansion with respect to volume, and it would look like this. And again, these A, B, C, and D are material specific and tabulated. You can look them up. Okay, so these empirical constants, like I said, they're tabulated in the back of the book. Those are 3 common ones to use. And if I do use them, it will be like a light version of, let's say, the van der Waals. I'm not going to go crazy with this for you. Another one is if I take PV over RT, that thing is equal to 1 for an ideal gas. If I instead say it's going to look equal to Z, okay, and Z is a number that's some number. If I plot it for some substance, let's say for nitrogen, when pressure is fairly low, for all of them, it's going to converge at around 1, which makes sense. That's the ideal gas assumption that the pressure is 0 and that the temperature is very high. So I could see here that these things approximate ideal gas behavior really well when the pressure is very low. But when pressure changes, it will no longer be 1. As you can see, kind of goes up and down, and it's really dependent on the material. And so people do this. They look at specific compressibility factors for a gas, and they can use that to find the state variables. So even though these look all different, what we've seen is if we normalize the pressure, the temperature, and the volume, okay, we normalize them with a critical point, which I mentioned before. That's the point where a liquid can no longer be established. Okay, if I divide the pressure by the critical pressure, I'll get what is called the reduced pressure. And same thing with the reduced temperature, and a reduced volume is not specifically what you think, but it looks like that. And what turns out is if I then plot Z instead of versus regular pressure, but by with respect to reduced pressure, I see that a bunch of different substances follow the same exact line, and that's known as the principle of corresponding states. So here E is ethanol and N is nitrogen, and P is propanol and W is water. And you can see that basically things follow that same kind of footprint for a reduced pressure of 1. More amazingly, this happens at a bunch of different temperatures and a bunch of different substances. So much so that people use these relations directly to find pressures and temperatures at different conditions. And it's not an equation of state. It is an equation of state, but it's not something you can specifically plug into. But you can look at a table and find out what that would be for your substance. And so this is extremely useful and is heavily used. And you can see as the temperature, reduced temperature kind of goes up and up and up and up, eventually you will reach a straight line, and that's an ideal behavior. Again, temperature high, low pressure, that's ideal gas behavior. So that's kind of cool to use. So let me show you some examples with those. Before I do that, let me just talk about liquids and solids. Those things are not compressible. So I can say that the expansion work is always going to be zero. And if there's any work introduced to systems where I only have liquids and I only have solids, then the work has to be in a different form. You can also assume that Cp and Cv are equal, and therefore that the enthalpy change and the internal energy change are equal. And those assumptions are then used for those. Now let's look at examples and see how these are being used.